Okay, let's go. All right, so good afternoon, everyone. This is the first BlinkOn in California that I was unable to attend, but there were good reasons for that. That being said, I'll do my best. I'll try to do my best to present the stuff we have been working on. Right, so welcome to RISC Business, Optimizing Chromium zlib for RISC V, or how I like to say, the story of 5 patches. So some mandatory notices and disclaimers. So why are we here? Well, to explain how the magic is done. Basically, without RISC V optimizations.
Yep. Nelson, can I interrupt real quick?
Yes.
Do you mind hitting present so that all your slides get bigger?
Oh, yes. Sure. No problem.
And the slideshow button just on your upper right.
Right. So what happens if I just press here to slideshow mode?
That's exactly right. Perfect. There you go.
Okay. Cool. Right. So the idea is to explain how the magic is done, how you were able to improve data decompression in average 49% on RISC V processors and about 12% for data compression on Chromium zlib. So the presentation structure, we're going to be talking a little bit about Chromium zlib. We will present a crash course on RISC V. Then we will follow through the optimizations proper. Right, so for people who are not familiar with, Chromium zlib is a fork of canonical zlib. It has seen the optimizations for both x86 and ARM architectures and now RISC V, and offers an average 3 times faster decompression and 60% faster compression when compared to canonical zlib. And we also managed to implement a hardware accelerated compression, which makes data compression average 8 times faster, only for Xeon processors with quick assist technology. It's been active development for the last 7 years. And the good thing is that the optimizations we have implemented, they eventually permeated the rest of the zlib ecosystem and is used pretty much everywhere. Right, so RISC V 101. So RISC V is open standard instruction set architecture, or ISA. The specs maintained on GitHub is easily extensible and is a typical RISC load store architecture. And the really cool thing about it is that it's free. There are no royalties for anyone implementing it. So think of it as the Linux of ISAs. So RISC V supports 32-bit, 64-bit, and 128-bit, and offers instructions in groups of extensions. So as an example, RV64GC stands for RISC V 64-bit, G, which is general purpose, which includes integer instructions, multiplication, division, atomics, floats, single precision, and double precision. The register file starts with x0 for 0 and x1 to x31 plus the program counter. And what is really cool is that the instruction set is always the same, no matter if, say, it's a RISC V implementation on 32-bit or 64-bit or 128-bit. And the manual is available on GitHub. So this is like the register file. What I think is cool is that the registers, they will have meaningful names. So as an example, argument registers, even though they're like x10 to x17, they will be named A0 to A7, which stands for argument. So that's pretty intuitive. So here is an example. as a typical RISC implementation, RISC ISA, you have an operation followed by a destination register and say different arguments. So if say we look at the assembly generated for a simple add function in C with two arguments, we will have the assembly generated by Clang as a add W A0, A0, A1, right? So we grab the two arguments passed by the function, we add them, and we store on the A0 register. Cool. And this is how the same function looks like on the instruction set manual. So people have an idea how the documentation should look like. And it's really cool because if, say, you are familiar with other RISC architectures like AR64 or ARM, the assembly is going to look quite similar to some simpler instructions. And just to make things funny, this is what the assembly looks like on x86-64. In case you are wondering, LEA stands for Low Effective Address, and the RDI and the RSI stands for Register Destination Index and Register Source Index. So it's I would say it's an interesting instruction that allows you to add up to 3 arguments, or if I recall correctly. And you can do stuff like add and multiply one of the arguments by a constant. You can exploit it when, say, you're accessing elements in a array, so on. So, yeah. So, mandatory mean used to be a traditional BlinkOn. Basically, RISC ISAs, they are going to be similar, and that is kind of expected. All right, so let's talk about compression. The decompression optimizations in Chromium zlib can be split in 5 different optimizations. One is about checksums. The following one is about when you are writing decompressed data to the output buffer. And the other ones, they are related with RISC-V and condition decode of literals. RISC-V is when you are reading data into the decoder, and the code of literals is when, say, you are, if I recall correctly, processing a literal, because basically LampLZ set 7 is going to split data on literals and pairs. And finally, using a flatter Huffman table, which should be portable. But it's interesting to pay attention that a chunky copy RISC-V and the code, conditional decode of literals, they are organized together. All right. So what I think was interesting is that when I started by looking into what is a perf trace in a typical x86 processor versus a RISC-V processor running a zpipe, which is a helper application that uses the zlib format for data decompression, we know that most of the cycles spent on x86 and especially on AR64, they are related with zlib proper. But on RISC-V, we actually have lots of cycles being spent on kernel stuff, as also some dependencies in other libraries. So I think there is lots of work to be done on optimizing RISC-V. Okay, right, so what was the first patch? The first patch required was to actually make sure that the build system, because we have 2 build systems on Chromium zlib. We have the CMake build system, and we have the GN build system. First thing we had to make sure is that the build system would actually work for a second architecture. I added the CMake build system when I was hacking on Xeon specifically, and that helped me to better understand what would be the requirements for RISC-V. And The following patch featuring code was related with performance features detection. So similar to ARM, RISC V may have extensions, and we have to detect them at runtime. And we have to specifically detect the presence for RISC V 1.0, which stands for RISC V vector extensions, and also add some support code for guarding the optimizations. The following patch was more interesting, where basically Alex Young from Sci5 implemented a vectorized other 32 checksum. I believe he contributed that to a zlib, which is another fork of zlib. And the average performance gain for decompression using the zlib wrapper, which is important for, say, decoding PNGs, was 14%. But the performance gain for compression was just around 1%, which somewhat expected, because when you are compressing data, you have like smaller vectors, smaller inputs than when, say, you are decompressing. And this is how it looks like for the Snappy data corpus plus the Linux kernel source and what I call the JavaScript data corpus for compression. Wasn't that impressive, not great, not terrible. But for decompression, on the other hand, was pretty nice. I mean, as you can see, for HTML, the performance gain, I believe, was like 22%, almost 24%, faster data decompression. The following patch was contributed by Simon Hosey. The basic idea is that the chunk copy allows us to perform a wide load and a wide store when we are decompressing data. And it works really well when we have architecture with fixed vector lengths. But doesn't work so well on architectures or that feature varied vector lengths like ARM SVE, RISC V, RVV 1.0, or AVX10. So an alternative to handle this situation was what we call the generic chunk copy, where basically we rely on the compiler versions of main copy and main set to perform those wide loads and stores. And this was a blocker for two other optimizations, read64, which was an idea by Nigel Tal, and unconditional decode of literals, which was an idea by Dougal Johnson. And the average gain was pretty good. I mean, we managed to hit 9.5% faster data decompression and up to 60% for HTML. And this is how the data looks like for the Snappy data corpus. When you combine all the three optimizations. And the next patch, this patch had an issue though. It requires support for unaligned loads of scalars and vectors. And turns out that a RISC-V processor can actually implement only one of those features. And turns out that Clang actually had a bug on older versions, they say Clang 18. Fortunately, as part of RISC-V software ecosystem, which is a project hosted by the Linux Foundation. I have been contributing as part of the System Libraries Working Group. One of the members, he was like a LLVM Clang contributor, and he managed to fix this issue on Clang. Right. So after we had landed the first Adder32 implementation, Simon Hose contributed a really cool alternative way of computing the same checksum. Work on 22 iteration batches, and was actually 20% faster than the previous one. The average compression gain wasn't that expressive because there is a factor of 10x when, say, on a typical zlib wrapper, when, say, you make a checksum, say, I don't know, like 20% faster, we have to divide that by 10, so you're going to have an improvement in real data decompression around 2 to 3%. But it still was pretty good, and it was faster, and didn't had some issues of the previous code. But if you guys recall, the second slide of my presentation, I promised 5 patches. And we have discussed so far only 4 meaningful patches. So one of the patches was actually came for free. Last year, I landed a better insert string that used multiply add as the hashing mechanism. And the good news is that that's portable. So basically, we got this optimization for free when we were targeting RISC V. And there was a suggestion by Noel Gordon. So what was the work we actually managed to deliver? We achieved an average performance gain of 49% faster data decompression. And that's about 3 generations of silicon. And we also achieved 12% in average faster compression. But we still have some work to be done before we call the RISC V port complete. All right. So now I'm going to share some general remarks on RISC V for people who might be curious about it. So the good, the bad, and the ugly. I really like Western movies. So the good, there's lots of community-created documentation. So as an example, this link points to a viewer where you can say type intrinsics, RISC V intrinsics function, and see what are the arguments. The architecture also, because it's starting fresh, doesn't have lots of historical baggage. And RISC V may become in the future the Linux of architectures or not. I mean, if you go back in time, say 91, 92, no one could actually say how successful Linux was going to be, right? And as you guys saw on of the perf profiles, there's lots of optimization work to be done, both on system libraries as also compilers, the kernel, and everything else. Now, the bad things. I have to be honest, development tools, they are not great. So expect stuff like compilers to generate wrong code, expect stuff like perf not working correctly, and so on. Also, hardware supporting the vector extensions, RVV 1.0, is kind of hit and miss. Currently, there are only 2 RISC V boards available that implement RVV 1.0. And last but not the least, expect bugs and some limitations. So the ugly. The other day, this was published in the register. So a RISC V CPU had a pretty serious security vulnerability. So basically, using the vector extensions, using vector loads, you could actually load them and store. You could actually read and write physical memory bypassing the MMU, which pretty much is a big no-no, because even if, say, you have support for extensions for supporting virtualization. If say you can just bypass that, that's pretty bad. So expect some growing pains. All right. So some conclusions. Chromium zlib now has RISC-V support. The compression work is pretty much near complete. What I think is still pending is implement a faster CRC32 checksum using the new upcoming crypto extensions. Probably the code we have today for x86 could be ported using this instruction, I think, using the Barrett property. Compression still pending some optimizations, but I don't expect major improvements, something maybe around 10%, 14%, give or take. And as always, pets are welcome. And I have some special thanks here. I would like to say thanks to Nathan Eeg from Google. He shared with me a RISC-V QEMU image and also access to a K230 board. That helped me a lot because instead of, say, spending like weeks to set up a RISC-V development environment, I just got like a QEMU image that had everything to start hacking. So thanks, Nathan. Also like to say thanks to Simon Hosey. He contributed to core patches that improved a lot the performance of Chromium zlib on RISC-V processors. And also like to say thanks to Jean-Luc Gailey and Mark Adler, who created canonical zlib. Especially Mark Adler has maintained it for the last 29 years for free. And the last but not the least, I'd like to say thanks to my family, especially my wife and my daughter, for being so understanding of my zlib obsession. And in case you guys are curious, that is the K230 RISC-V board at the side of a Raspberry Pi 5 board. The K230 was fundamental to be able to develop these optimizations. And as you probably can see, I added some heat sinks on it, but I think I overdid the thermal paste. And with that, I think I covered everything. I will open for questions. I don't know where the questions are going to be posted. Yeah.
I'll be running either questions internally or over in the chat. So, do we have any?
Sounds good.
Yes, got a question from the audience.
Hi, thanks for your talk. Noting that you work at Intel, does your talk say anything about Intel's interest in RISC-V?
Well, yeah, that's a good question. So I mentioned RISE, which is a RISC-V software ecosystem. It's an initiative hosted by the Linux Foundation. And RISC-V is one of the founders of RISE. Also, fortunately, my manager allows me to divide my time between making zlib faster for Xeon processors and also playing with other ISAs like RISC-V. So I would say maybe I spent, I don't know, like 3 or 4 weeks on it. It's less than 10% of my time, really. Besides, I mean, you can actually become a better programmer if you start studying other ISAs. I had experience on R. I joined Intel to actually learn more about x86 before. And now there was the opportunity to hack RISC-V. And I welcome that.
All right, we have another question from the audience.
Hey, I had a general question, and I'll preface it by saying I don't know that much about performance optimization. I don't have too much experience, but it seems like a common theme amongst optimizations that I've seen is people go into a code base and then introduce like SIMD instructions or other specialized instructions. And I was curious, why doesn't the compiler seem to do a better job in like utilizing these instructions, and why is there such a benefit from like people kind of hand rolling the code with special instructions?
Okay, that is actually a pretty good question. So the zlib code base is really old. Just to have an idea, most of the decompression code was written around 95, and most of the compression code was written around 89 to 99. So the code base is performant, it's highly portable, it's highly efficient. But to have an idea, I mean, until like I think was last year, it was still using Kernighan RISC C style, right? So it was optimized for processors that are long gone. And the way the code was written basically makes the life of a compiler really hard to try to auto-vectorize the hotspots. So basically, that is one of the reasons why the compiler cannot help you much here. And my other guess is that maybe the fact that data compression is kind of a trick subject. Maybe it's not like optimizing a title loop in an add function with a vector. I mean, the compiler can actually do a really good job there. So maybe those are the reasons. And I think I mentioned that I have been hacking on zlib for 7 years already. When I started, I thought I would be done in like 7 months, right? And thanks to contributions from many people, we managed to squeeze lots of performance of a really antique code base. And we had lots of fun doing that, really. Lots of hours reading assembly code. But if you look on other projects, like the VLC project's a good example, the majority of their code base is handwritten assembly, right? So sometimes when a performance matters, you don't have much choice, right? You need to get your hands dirty.
All right, I think that's it. Thank you very much, Adam.